Welcome to our astrophysics seminar, and today we have the great joy and honor to have Dr. Angelos Vourlidas with us. We share the same alma mater, as we both got our bachelor degree at the Aristotle University of Thessaloniki. But Angelos has left our beautiful homeland for United States of America. So he is now a member of the principal professional staff at the Johns Hopkins University Applied Physics Laboratory and the section supervisor in the Space Physics Group at APL. Angelos received his PhD in 1996 on ground-based radio observations of the solar corona. And after a brief postdoc at Caltech, he moved to space-based coronal observations at the Naval Research Laboratory in 1997 before joining APL in 2014. His research focuses on the physics of the solar corona and on solar eruptions, and in particular on the phenomenon of coronal mass ejections and their influence on geospace environment. Angelos is heavily involved in space instrumentation and science management. He is the project scientist, the stereo SETI instrument suite, the Whisper imager on the Parker Solar Probe, and the Solo High imager on the Solar Orbiter mission. So he's the guy in the three seminal solar mission of our time missions. He led the calibration and integration of the SETI Core 2 coronagraphs and was the PI of NRL's Volt 2 and the project scientist of the various sounding rocket payloads. Angelos has authored or co-authored more than 230 peer-reviewed publications with over 11,000 citations. So thank you, Angela, for being with us today. And the floor is yours.
Thank you, Yanni and Maria for the invitation. I'm always happy to see my friends in Greece and talk about the stuff that we do here in the States and to be helpful any way I can. So before I start in the talk, I want to say to the students in the audience that if they have any questions about studies in the US or life abroad and as a scientist, they can always feel free to reach me by email or Zoom or whatever they prefer. So today, for today's talk, I chose to talk to you about my favorite subject, of course, the explosive sun. But given that this is an astrophysics colloquium, I try to expand a bit the scope and try to connect this to astrophysics. Basically, I would like to give you an idea of why we study the sun as astronomers or astrophysicists, which is our specialty, and that it's not just something that is isolated to a single star. Because of that general scope, I'm not going to go to too many details, and I see a lot of my expert friends in the audience, so they can tune out for a while. Although I'll try to be controversial occasionally, so that maybe we have a discussion in the end. But this talk is really focused towards students, undergrad students, and try to give a very basic overview of solar explosive physics. So I start with what we do, and what we do is build instruments that take these images and more that I will these movies and more that I will show you during the lecture. This is a particular in the EUV, and what I try to do is basically try to give you an idea what is that we see in these images other than pretty colors. So we're going to start from the basics and get an idea of the scales that we are concerned about. And so here is the sun in the visible. This is the sun that you might see with your own eyes if you don't, if you could otherwise. But of course, it's very bright. And so that's an image we taken from space, and that's quite homogeneous. It's just a white or yellowish ball, and it has a single, as we call it, sunspot on it. And when I give you a sense of scale, here we're comparing with Earth of what we're talking about. So this is a composite of images from different telescopes on the ground or in space. And as you can see, that small blemish on the sun is quite large. This is much larger than the Earth. And we have the ability, of course, with our telescopes to look at small details. And what we call small details is basically maybe mountain ranges size features on the surface of the sun. Now, the key point here is that really what we see in this visible light image is nothing more than a manifestation of the magnetic field evolution inside the star. We of course know that, or you might are familiar with the 11-year cycle of solar activity, which means that the number of these sunspots increases and ebbs and flows with every 11 years or so. And this simulation from NASA tries to demonstrate that what we see as those black blemishes, they're nothing more than the magnetic field lines basically bending and stretching coming out from the interior of the sun. And because the magnetic field inhibits sort of motions, generally speaking, these patches are cooler than the surroundings, and that's why they appear darker. The temperature of the white sort of sun is about 5,500 Kelvin, and these spots may be 500 Kelvin or 1,000 Kelvin cooler. Now, this, of course, you can consider, of course, the sun as a giant magnet, liquid magnet, of course, rotating, with the spore rotating and twisting the magnetic field lines, and that's why they basically pop up through the surface. But the motion does not stop there; it keeps going. And if we were to trace those field lines outwards from the surface, you can see the lower right picture, and I hope you can see my cursor. This is a magnetic field map of the sun, where the sunspots, what I saw there as visible light, is now replaced by values of the magnetic field, and where white is magnetic field coming out, black is magnetic field going into the sun. And so if we trace those field lines, you can see that the mapping features that we see in the upper corona of the sun, and those we take through ultraviolet light filters, which means, of course, that if it's in the ultraviolet, it's hotter. And you can, I can give you a rough estimate of the temperatures we're looking at. Here in the red is about 80,000. In the bluish color, we're talking about maybe 600,000 to 900,000, and then in the yellowish gold, we're talking about 1.4 or so million, which is sort of the temperature at which most of the sun's outer atmosphere, the corona, most of the material in the sun's outer corona is heated at. So you can see that the magnetic field in a way structures the outer atmosphere of the sun in very intricate ways. And then that does not stop there either. If we continue outwards, well, we have the sun here in the upper left corner, the sun that some of you may be familiar if you witnessed an eclipse, where we see these bright rays that we always represent in cartoons. That's how we represent the sun in the cartoons with its rays, which are basically plasma, material of the sun flowing outwards. And those rays are structured, again, in radial, more or less radial structures. And as you can see here in the middle of the lower panel, those correspond to the magnetic field lines keep going out into the corona. So the magnetic field is really what determines, in most cases, what we see with our different telescopes in different filters. Now, this again does not stop here, and that's really where we come in this picture, with the Earthlings. The sun, the magnetic field encompasses Earth as well. Here is a very simple-minded of the what we call the current seat, where the magnetic field changes polarity from one direction to the other. So, like if you think is if the sun is a bar magnet, is the area where the field changes orientation. It has a structure to it, as we already seen, that is a bit simpler. As we go farther away from the sun, that structure tends to simplify because there is other interactions that I'm not going to discuss today. But you can think of it as a blanket, really a magnetic blanket that also encompasses Earth. And that means that if there is some change in the solar surface or solar corona that kind of moves this blanket, well, this creates ripples and other effects that we, of course, sense at Earth particularly in our outer atmosphere, in the magnetosphere, which is sort of the cocoon that tends to protect us from a lot of the direct impacts of the sun, of the solar variability. Now, this changes in the outer magnetosphere. Of course, they cause instabilities in the magnetosphere. The magnetosphere then interacts with the lower layers of our atmosphere, creating other effects which we collectively call space weather. And you might have heard about the effects it might have in communications, flying over the poles. You might see enhanced particle fluxes and storms. That the most beautiful manifestation is the auroras in the poles. So this is really the connection to everyday life. We want to understand why the sun evolves, and particularly when it makes very sudden changes, sudden releases of energy, because in the bottom line, some of them might affect us in our even day-to-day life, particularly now that most of us, or all of us, are relying on cell phones for much of the information that we get. So this is the practical part, but then of course there's the beautiful part of all this, of being a scientist. And if we were to only observe the sun with the visible light, of course we will see the sunspots, and you are familiar with that. And as I say here, it's like watching sunspots grow. Okay, it might be mildly interesting, but I think it's a bit boring. There is a lot of stuff happening in this picture, but your eye does not pick it up. However, if you move higher up in the corona, things are a bit different. And here is a movie that I made from our telescopes on the stereo mission from our extreme ultraviolet telescopes, where I combined two temperatures, one in silver, which is the hot plasma, and one in red, which is the cold plasma. So kind of taking the two extremes in the corona and combining for the whole month. So you can see here with 2 hour cadence, 1 hour cadence. And so as you can see here, there's a lot of stuff happening in the corona over that month. This is during a period close to the solar maximum, not quite yet, but as you can see, you see this plasma manifestations of the magnetic loops, what we call the magnetic field lines, changing, erupting very suddenly. You see material leaving the sun here in the periphery over the limb. And in generally, you see holes opening up where the field is, the plasma is cold. That's why it looks reddish. And others where the images are bright, when it means that the plasma is hot. So that tells you that there is maybe a different energy involved. Now, these manifestations that are, as we call it, low in the corona, they become even larger in the outer corona. And here is, again, a similar image with a 15-minute cadence of the corona. Basically, if you had a solar, if you could see the sun with a continuous eclipse, this is really the day-to-day corona that is that the sun is presenting to us pretty much every day, and that's really what I do. This is one of the instruments that we built back at NRL, where the inner disk is about 2 solar radii, 2.5 solar radii from the sun center. So we're seeing basically the outward manifestations of all this evolution that I showed you in the previous slide, and that's in the visible light. So this is indeed what you could see with the naked eye, if of course you could block the sun so efficiently. So the bottom line is that the sun is active. It's very interesting. There's something happening every day. That's what I do pretty much every day. I already checked the evolution for the last 2 days to see what ejections have happened in the sun. Now, because this is the corona, we call this ejections coronal mass ejections. What we see here with the brightness is basically reflective light from the photosphere on the free electrons in the corona, and therefore the brighter a particular region, the more mass in electrons, and presumably in protons it contains. So this coronal mass ejections is really the, if you like, the main connection between what's happening in the sun, the energy release on the sun, and how the heliosphere feels that energy release. That's what comes and impacts a planet and may disturb its magnetosphere, or in the case of Mars, may strip away its atmosphere. Okay, so this is the main connecting link between the star and its planetary system in terms of interaction. Of course, the day-to-day solar wind that you can actually see here, and you can see even better in the next movie, which I now this is really the big view, seeing everything between the sun and the Earth, and that's taken from our telescopes on stereo, where I combined both stereo spacecraft data from both stereo spacecraft, so I can give you a 180-degree view of the inner heliosphere. And to me, this is the movie that shows why we care about the sun and how important it is to us. You can see several of these CMEs that when they come towards us, they appear as a big halo, we call them, as a big, circular, more or less, bubble. And this is actually Earth, which is quite bright, so it saturates our detectors. But you can see that this phenomena as they go towards Earth. So we have this observation, these coronal mass ejections were detected for the first time from NRL back in 71, December 14 was the first detected coronal mass ejection. They have been seen indirectly in radio before that, and with other types of phenomena in the sun, but it was never recognized as that a coherent, such a large scale coherent structure could actually be sort of emanate from the sun on a regular interval. We have now 50 years almost of observation, 50 years of observations of coronal mass ejections, so we know a lot of things. Here are some of the statistics that I regularly put together from a particular instrument from the LASCO, which is a coronagraph that is along the Sun-Earth line at the L1 Lagrange point. And it's been operating, as you can see, since '96. And so we have almost 2 solar cycles, well, 2 solar cycles actually of data. And here I have the mass in the upper left corner, the average mass of the CMEs. Here's their speeds, and in this big, the bottom panel, I have the total ejected mass in coronal mass ejections per rotation of the sun per month, if you like. So it's about, as you can see, 10 to the 16 grams per month, which it's a big number, but it's not that much compared to the solar wind. The solar wind, what is sort of emanating in a more quiescent way, yet intermittent, is probably a factor of 10 larger than that. Although we haven't gotten an exact number quite yet. So you can see, of course, that the speed of this phenomena changes and really varies with the number of sunspots. So that tells you that it's the complexity of a magnetic field plus the intensity of the magnetic field that, in a sense, drives this activity. So again, the magnetic field seems to be the the defining characteristic of all that. So what do we know about CMEs? I mean, this is now, I'm going to condense 50 years of research into one slide. How these things happen and how the magnetic field actually makes them happen. Well, I'm an observer, so I like cartoons. And so I use here 2 cartoons based on modeling. And these are older models, but the general principle has been verified with the latest and greatest images that we have taken. So basically, what we have here on the right hand side is the ejection of the CME is an ejection of a magnetic structure called the magnetic flux rope, which in its cartoonist most basic I guess mathematical representation, if you like, is nothing but like an induction coil or a slinky toy. Of course, in reality, it's a little bit more complex than that, but this is what we use as our sort of working hypothesis. So this magnetic is basically a purely magnetic structure. It has a magnetic field. Its morphology is described by a parameter called helicity. So those 2 parameters, the interplay between these 2 parameters and the surrounding environment, which is also magnetic, sort of determines or possibly drives when an eruption is going to happen, which we don't yet know, and how dynamic that eruption will be. Of course, you have to have enough energy, magnetic energy, available in the corona to power this eruption. So we expect that bigger active regions with more complexity and bigger sunspots will be the sites of bigger eruptions. Now, as this flux rope goes up, you can see here is called the connection outflow. The magnetic field lines behind it coalesce, and they change topology as they interact, which releases additional energy, which is basically pushes the CME out and also creates particle beams that go towards the lower atmosphere, heat up the atmosphere, and that's when we get very bright, very dense or concentrated loops that we call flares. And here on the left-hand side, you can see kind of like a 3-dimensional view of the same cartoon, where as the flux rope, which is a 3-dimensional structure, goes up and expands, we also see an expansion of this current sheet behind the flux rope, the reconnection region behind this erupting flux rope, whose foot points are manifested as what we call ribbons, brightening ribbons that we see in different temperatures and wavelengths, expanding from, in principle, the center, but now you have to be a center. Now, as this flux rope, you can think of this flux rope as a magnetic obstacle, a plow. It picks up a material around it, so it piles up density, and that makes it creates this. What I'll show you. So what we expect to see is basically a density drape around, and in a sense, a relatively empty flux rope, because the magnetic field kind of inhibits plasma from coming inwards. And there are many more details here that we can discuss later. So what do we see in the images? And so this is one of my favorite CMEs, of course. In slow motion, we're combining again all our telescopes. And this is, to me, what CMEs look like. I think it should be quite obvious that this looks like the density manifestation of a helical system. And here is also my modeling approach here, my simulation, where I take the images from Core 2 and I project the cartoon, and you can see the correspondence. So in of course, the devil is in the details most of the times, and I'm sure people may disagree on some of the details, but I think the big picture has been established, that what we see, at least in the coronavirus, is that the structure of the CMEs is a magnetic flux rope, and a lot of that goes out in the sun. That's what the sun wants to do. It wants to eject excessive energy and helicity into this form of magnetic flux ropes, and that's what we get, coronal mass ejections. We have manifestations. We have actually captured the formation of these little flux ropes right at the start of the event. Here is a very pretty movie, again, of combining two different wavelengths in the EUV. In red is something that is extremely hot, 10 million degrees. And you can see that this red structure appeared almost purely red. That means that it is isothermal in a sense of 10 million degrees. It does not exist in this, we don't see it in that golden greenish background, which is 1 million degrees roughly. And you can see that it appears at some point, and the movie goes for 6 hours. It's very hot and seems to diffuse, and then suddenly we get a reappearance, and we see basically what we see in the cartoon to the right. Right? It's basically like a real world movie of the cartoon. And so this is, of course, it was a fast event in the center of the active region. So people can say, well, maybe this only applies to very intense magnetic fields. Well, this is a picture at some area of the sun that has almost a very weak magnetic field, almost zero, we say. Of course, it's never non-zero. And what you see here is, again, a much slower manifestation of the same event. You see a hot balloon, if you like, with a cold plasma here in the red behind it that is slowly rising and taking some of the cold plasma along. But again, this gives you the impression that you're seeing this flux rope kind of from underneath at an angle. Okay, so so this is really the grand tour of solar physics, at least of CMEs. Now, as I mentioned earlier, this phenomena are really what the main drivers of space weather. And what we know about them, I mean, it can be summarized in those sort of 6 bullets that I have over there. Usually, the big events that we maybe we're concerned more from a technological or societal point of view are big events that happen on the center of the disk. They create very bright flares. Then we see a huge halo-like CME associated with also with very highly energetic particles that impinge our telescopes. And of course, these are the ones that are dangerous, for example, for astronauts, say in cislunar orbit or on the way to Mars, because most of them are blocked by the magnetosphere, although some of them penetrate. And so that's also an issue, particularly in higher orbits above LEO. We know this happens in hours, which in the scheme of things is probably short. And we generally have about 3 days to react when talking about the CMEs that are not too fast. The fastest one we have recorded is about 18 hours, I think 17 hours, that occurred in July of 2012. So there is not much time to react, really, if you're running a business or you care about emergency management. And so that's why a lot of us, Yanis included, Tassos, have been looking at the response of the magnetosphere and trying to devise ways that we can maybe predict or forecast better the effects of those phenomena. But this is really now like I said before, the link to the exoplanet. So events like this don't happen only on the sun. We assume that the stars they are more or less the same. Of course, you have different temperatures, metallicities, and some of them might not have dynamo, but let's assume now that what we know about the sun generally applies. Then when we look at exoplanets, I guess one of the first questions one will ask is, are those habitable? Is there a reason to invest resources to check the planetary systems for life for signs of life? So the way that we usually go about this, and again, I'm trying to summarize, I guess, the whole field of exoplanet research and the connection to the solar very quickly, is basically like we know from the sun, all the activity happens in the stellar corona. Therefore, what we care mostly is the magnetic, of course, properties of the star and whether it has a corona or not. Now, assuming that it has a corona, then we go and we think that we have two big eruption signatures, energy release signatures, are the flares, because the irradiance, for example, affects the lower levels of our atmosphere, for the mesosphere or thermosphere, and CMEs for what I already discussed, the magnetic obstacles that come and impinge on and carry particles with that. And so we have, I can think of 4 ways to monitor for these signatures in other stars. One is to look at, of course, irradiance changes in the full wavelength that we have in our astrophysics missions, from soft X-rays to visible or even infrared. For the CMEs, and that's easier to do because, well, we've been studying the stars through the light for forever. For the CMEs, though, things are a bit trickier because what we want to do is detect some sort of a motion in the planetary system. So we have to look at outflows or Doppler shifts relative to the stellar motion, dimmings, because as the CME removes part of the stellar atmosphere, so create dimming, and of course shocks, which I didn't mention. They do. We can record in radio, and radio we generally have sensitive radio instruments for stellar astrophysics. And so, to see what we should expect, the only thing we have really is the sun, right? We don't know of anything else. So we have to find a way to extrapolate from solar observations and connect flares and CMEs, because flares really will be, practically speaking, usually our main workhorse, I believe. So for the flares, here is the current status. We have no detections of CMEs. Of course, we see flares from other stars. We don't know if those are eruptive flares, if they are associated with mass ejections. And we have no radio observations that show a drifting structure. The way to go from the solar stuff to the stellar stuff, well, one is to look at flare rates and say that, because we know from the sun that if a flare is above a certain energy, almost always 100%, like I say here, it has 100% correlation with the CME. So if we could somehow scale the size of the flares on the sun to what we see in other planets, maybe we can use that as an indication of CMEs. Radio bursts, they only give us a lower limit. Again, it's a tricky issue. Now, the sunspot properties, like I showed earlier, they seem to be a very good, strong indicator of eruptive activity. So if we could actually map stellar fields, magnetic fields, then we will be in a very, very good position to transfer solar heliospheric knowledge over to other stars. Now that's some of the examples that the work that has happened. We know that at least in irradiance, most of the outputs should be invisible for the stars, but this is very difficult to measure on the sun because the sun is very bright and visible. So the flares make apparently a small change. But it is a way to go forward. More work needs to be done in this field. The other one is on the flares. Here's a nice example that puts the amount of flaring versus the volumetric energy. So the sun, as you can see, we can get to 10 to the 33 ergs that in 10 to the 30, I would say 10 to the 32 ergs for the sun in output, radiative output. And there are some estimates there that the stars could be going, the stars could be a factor of 10 or even 100 more energetic. They might have available energy, or maybe manifested in the flares that we see from them. Now, for the active stars, there's maybe a problem because our scaling laws do not match them very well. So that's again an area that somebody should take a look at. What can we do from the sun, though? What can we learn from the sun? So one way is to take the stuff that we know from the sun and and the models that we have, and try to see, well, let's push the models and see what would they predict if we added artificially more energy in the sunspots. So this is a collection of statistics. These are solar. The low part is solar flares. These are stellar flares. You see, there's a gap here in our in this connection, but we do. There are some of the brightest, if like more energetic flares of the sun. They almost make it to what we see from the stars. Still, there's a 2 orders of magnitude gap. In this work from Guillaume Molanier and colleagues, they did this. They took a model of a CME, and they basically tried to pump energy into it to see how big the flare will be. And so from and how big, what would be the percentage of the sunspot area that needs to be incorporated into, participate in this flare to create that output. So you can see here, this is the scaled sunspot cartoons of the area of the sun that needs to participate. And so here's the solar cases. These are sort of the typical sizes that we see in post-flare loops. This one, the 10 to the 33, may not have seen, or maybe we've seen it once. Now, to get to the stars, though, we need to have sunspots of this order. I mean, they have to be a considerable fraction of the star. And of course, there are magnetized magnetars that apparently the sunspot seems to cover a big area because we see drops in their light and the magnitude as they rotate. So it is conceivable that the same model maybe just needs to be extrapolated 2 orders of magnitude. But of course, being scientists, we always have to be wary about extrapolating our theories to such big numbers, because after we might not have witnessed the physics that may be relevant once you go to factor of 10 in physics, in field strength and complexity. There may be other issues about how the field interacts with the plasma, whether it can accumulate so much energy without breaking up the atmosphere apart, and so forth. But yet, I think we have to start from what we know, and that's the sun. The other thing we can do is look at dimmings. This is a typical dimming modeling from Meng Jin, looking at not a very particular big CME that we saw, but it was on the front part of the disk. It was witnessed with high cadence and resolution. And you can see the effects of the dimming in blue in 2 different temperatures. You can see at 0.6 and 2 million degrees. And so he tried to model this. You can see here on the right his models compared to the observations. And although they generally capture the output of the expanding dimming or wave, the amount of dimming that he predicts in the model is much larger than what we see on the sun. Okay, so this, as you can see here in A and C, for example, which is the cooler temperatures, 211, but not so cool. And so this, to keep that in mind. So then he takes this model and applies it to does the same thing, pumps up the energy to 100 times more. That's to see what would have happened on the sun. First of all, the good thing is that the outward CME is not really so crazy. The speed of the outward CME is still with what we see from the sun. But you see the amount of dimming that this will have caused, particularly 94 angstroms, which is potentially a very hot channel. is very extensive. So if this had happened, basically half the sun should have dimmed for a few minutes, of course, not. Now, if we look at the integrated density, you can see that the change is only 20%. So although it looks very impressive and spatially resolved, as a star, we're looking at 20% type of changes if we'd like it. So again, this is going to be a tricky thing observationally, but again, I think that the guidance from solar observations may help us fine-tune the observing programs for those that are interested in this. And finally, let's look at the CME itself, and that's what Ben Lynch and collaborators did. Basically, they assumed that the biggest sort of eruption that we know of in terms of impact on Earth was in 1859, a Carrington eruption. It was a big flare because we didn't have the same instruments then. So based on estimates, it was about the X45 flare. The biggest one we've seen is X28. So it was a factor of 2 bigger than what we have witnessed in the modern era. And so he said, well, what if I pump all the free energy that our models suggest, which is about 10 to the 34, pump it all into an eruption based on this model. Here is the view from the top of the sun of this of the corona when the eruption happens. And as you can see, the eruption basically goes all the way 360 degrees around the sun, basically explodes the whole current seat of the sun in the corona. So basically the corona in this particular configuration would have emptied completely and then of course refill. Low down are snapshots from his simulation showing here on the left the speed, and in the middle the CME, the density. So in terms of density, it looks like a regular CME. And this is also the compression. For those of you that are into shock physics, you can see that the compressions that we get is about a factor of 4, which is basically what the models predict. So it's not something extremely dense either. So that would be tricky to detect from farther away. So coming to the end, this is what basically we can do, or ideas that we can do from the solar side. The problem I had when I started discussing this with people at Space Telescope Institute, my problem was that most of the work that they do is focusing on M dwarfs. Well, M dwarfs are not the sun. They are very close to, they're totally locked to the star. And so just because they fall into the habitable zone, and no, actually, the reason they do this is because that's what they observe. And so they are kind of like the drunk person looking for his keys under the light. And when they ask him, where did you lose your keys? He says it was over there in the dark. And they ask him, why you look at the light? He says, because that's where the light is. So we're looking at I believe looking at the wrong side. I don't know how that could connect to really well with the sun. So this was my statements to them, that these systems are not really, to me, solar analogs. It would be better to maybe pay more attention to G stars. Maybe there are fewer, but maybe the analysis we do there may be more applicable. Okay, so for those of you that really want to go into this exoplanet, which seems to be quite the popular subject lately, including in our circles in solar and space physics. Well, that's what I was suggesting, basically, that we need to ask the solar and space physicists to go back to what we have gathered from the sun in the last 50, 60 years and try to analyze them with the mentality of an exoplanet, of an distant star, and see whether the lessons we've learned can be, or how could best be applied to guide research in exoplanets. And of course, for that, we do need to talk more to our astrophysics colleagues and trying to correct some misconceptions and also get input and see how this cross-pollination can help us move forward, because I think that's going to be a major major impact or thrust of research, not only for astrophysics, but also for solar heliophase physics for the new generation of scientists. So that's all I have. Thank you.
Thank you, Angele. So the floor is open for questions. You may either ask directly, Angelos, or maybe even write something in the chat box. Spiros Patsurakos.
Yes, thank you. Thank you, Angele, for the nice talk. I have a technical question. So you mentioned, okay, and that's the only way, of course, to do this is we have to get lessons from what we know from the sun. So regarding CME observations, of course, we can photograph CMEs using coronagraphs for 50 years, as you mentioned in your introduction. So what will be, how much what are the requirements you think of, applying similar kind of techniques, coronography, to hope to ever observe a stellar CME? It would be formation flight?
No, well, at the moment, it will be no. We cannot do it. We cannot do a direct detection of the excess mass of a CME. It would have to be either a Doppler measurement, like a spectroscopic measurement, or some other proxy, because we can barely detect the planets, and the CMEs are, I don't know, 10 orders of magnitude darker than the star. So this is not possible yet. I would expect to see them, like I said, either in spectroscopic techniques, or, well, what with radio observations, because they should be of similar power output as the solar ones.
Okay, thanks.
Sure.
Yeah, so it's a quite challenging. It's a big challenge for astrophysics to detect, to identify or to detect coronal mass ejections in other stars.
Yeah. So at the moment, from what I gather, we're focusing on seeing the impact of maybe the CME on a planetary magnetosphere, if we could, by looking at trying to detect auroras, or even mass loss, maybe again with spectroscopic techniques, I assume, or look at the dimming, because something that is related to the stellar light, changes in the stellar light, which there's a lot of experience with exoplanetary research, and I'm wondering if there's a way that we can cross-pollinate and come up with better measurement techniques there.
I guess this is not yet the objective of any ongoing mission, right?
There is a MIDEX mission under competition still, in the phase A, called Escape, that is, I think, geared to look at EUV, to do EUV observations of auroras. That's my understanding. From nearby stars, of course, that they have planetary systems.
Okay.
That's out of Boulder, Colorado, I think.
Interesting.
Yeah. And we're putting together at APL, I mean, not me, particularly, I'm not, also ideas for the NASA asked for new mission concepts, which would basically drive our decadal, our 10-year plan, science plan. And a lot of people are very interested in that sort of looking at the solar system in a way from as an exoplanetary system. Was look at the Earth and the giant planets and try to create, make measurements that would be applied to astrophysics.
Yeah, that's these are very interesting perspectives, I believe, and I guess they will, in the near future, we will be seeing such missions being implemented.
To me, it's almost inevitable, given the popularity of the subject, of course, for the public, and the benefits of how interdisciplinary will allow at least NASA, for sure, for the divisions to start talking to each other, including planetary, helio, and astrophysics. This will, of course, fall apart, as you can imagine, when it comes to funding. But as long as the scientists are involved, yeah, there will be great ideas coming up. So yes, but I focus on that because I think for the next generation of scientists, or the people that are now undergrads, this would be quite a big field potentially. Whether they do astrophysics or they come to our heliophysics fold.
We have Manolis Georgoulis and Evangelia Samara. Manoli, would you like to start?
Thank you, Yanni, and thank you, Angelos. That was an interesting talk and an interesting take. I noted from your presentation that we have different ways of. We need to extrapolate first of all, but we have different ways of doing that.
Mm-hmm.
And there are a number of unknowns in this respect. In terms of astrospheres, for example, you mentioned helicity at some point. Helicity is important because of its conservation property, but you have to have the right plasma. The right plasma meaning you have a high Reynolds number, low beta plasma, so that to be able to materialize the helicity conservation principle. So my question is, and you mentioned also that M dwarfs might not be the most appropriate target here. What is the role played by the astrosphere, the condition of the astrospheres and the different kinds of astrospheres in the propagation of these events, and whether it is right to go ahead and say that whatever comes out, I mean, if we go as a sun as a star, we're going to be getting similar results to what it should be. So there are a good number of unknowns, and I don't know if there is any comment that you can do on that, and whether there is any point in using the sun as a model star, or perhaps going into other stars and assigning different assumptions in there.
Yeah, that's why I make the comment that we need to go after G stars, because the astrosphere is the important thing. I mean, if the CMEs are coronal, therefore that's the only thing we care about. But you know, whether we only know about dynamo-driven stars with convective zones. So I think that we should be focusing on stars that are similar. Yeah, well, we know that somehow they have convection. We know that they have maybe a sunspot cycle. So one effort, if I was to strategize about this, I would direct one effort towards mapping the nearer stellar neighborhood, and identifying the best candidates for stars that are they're so similar behavior to the sun, that we either know that they have dynamos or they have filaments by looking at doing an H alpha or Lyman alpha survey, and they seem to be. I mean, this requires long-term studies, but they seem to change not in some weird way that they might have a binary companion and stuff like that. So, and then focus on those, exactly like you say. Then at the same time, though, of course, I would look at stars that are not quite like the sun, that they might look like slight different deltas. Either they have a irradiance variations that are a little bit stronger than the sun, or they have bigger star spots, and again that they're by themselves, which will be hard to find, and see what phenomena I get there, and whether I could now start modeling them with our existing, take our existing MHD and whatever we have modeling, and push our modelers towards that, to start investigating what other physics I need to introduce to match those flares. That would be my two prone attack. But yes, I would stay away from M dwarfs. because like you say, something that's still tidally locked, I don't even know what physics I'm supposed to do there. Sure, if you have a binary star, they might have a loop that goes across the stars. Maybe that's the same as two sunspots. Sure.
Right. In case of tidal locking, as recent work by Evangelos and Mara showed, it is quite likely that tidal locking, because of the slow rotation rates that it corresponds to, may mean that planets may be able to sustain a weak magnetosphere, if any, which means that it's going to be swept away by stellar CMEs, particularly in the higher end of stellar CME parameters. So it is indeed an issue there, but it's useful in the sense because it tells you what really matters. I mean, parameter studies like that tell you what really matters in this respect. So they may be able to point you toward more appropriate case studies that could give you a number of clues in the future.
Okay, and measurement approaches. So that means new instruments. You know, I always have to think about new instruments, right?
Yeah. Thanks.
We also have Evangelia. Evangelia, please.
Yes, hello. Congratulations, Angela. Very nice talk. I think I was actually covered by what Manolis asked before, and I'm not sure that I have a question anymore. I would say it's more like a comment. For example, if one is focusing on M dwarfs, these are stars that are much more active than the G stars. Okay, so I think it's at least a bit safer there to correlate the flares with CMEs. So I understand what you're saying, that we should really turn into more solar analogs and not so much focus on the M dwarfs, but maybe it's what we have right now and it's the safest way to go. And once we have more data and more observations, then we can change what we have, and maybe we need to update our findings and our results. So I'm not sure if it's totally wrong to look into M dwarfs. Well, even if things change afterwards.
Like I said, there's the tidally locking that bothers me. That really is a very big difference with what we have in our system. Our system is just a single star, so I would stay away from all binary stars to begin with. But you know, like that's what I said. You know, the people working on this, like the drunk person. You know, that's all they got. They have to work on that. They have to publish, right? But I'm talking about what matters and the use of the limited resources that we have. And I think, at least on the solar side, we should be more careful when we interact with them. That we should be the ones that guide the exoplanet habitability research to more logical ways, if you like. You know, we should give them our experience and direct them away from these things and point to what should be the proper stellar analog, or how the solar stuff should be interpreted. You know, I think that there's a very like a Wild West attitude in that field. Just take whatever they see on the sun and extrapolate it.
Yeah. Okay. Thank you very much.
Yeah.
Okay.
Hi everyone, I have a question. You have shown in slides about the flux rho. I want to ask that what are its consequences in coming years that we can see from Earth? That what will happen? Is there any chance of any big blackout or something?
I didn't catch the question.
We cannot hear you. If the sound connection is not so good.
Hello, am I audible?
Perhaps you could type your question in the chat because we cannot hear you very well. Can you type your question? So in the meantime, may I ask something? till we,
Yes, of course.
So you mentioned something about the simulation and the dimming. And if I got it right, you mentioned that the simulation was predicting much more dimming than the actual observation. And despite that difference, this kind of simulation model was used to other stars to make some predictions. So I was wondering if you could say a few more words about what is the main reason for this difference, because it was quite large, and what is the main reason for that difference?
Yeah, that's a good question. It goes really to the heart of the modeling of the coronal heating modeling. You know, this is one of the big open issues in solar work. And the models, as you can see, the magnetic field models that we have, they seem to do a pretty decent job in capturing the structure. However, when you want to transform this structure of field lines into what we actually see in observations, which is plasma heating, you know, all these loop-like features and how the brightness varies in X and Y and in time, that's when the big gap opens. And that's because we don't have measurements of the actual magnetic field in the corona. We use extrapolations. And we don't have a holistic understanding of what drives the coronal heating exactly. I mean, it might be magnetic field reconnections or waves or a variety of mechanisms, but they matter. And so to capture, so the end result is that the models cannot capture the amount of material at a given temperature well. And therefore, when they try to eject that material, obviously, you know, you're going to end up with big discrepancies. So that's what really, as you can see in the right-hand side, these four images are at different temperatures. And so some of them correspond better to the observation, some not. So that kind of tells you that, I mean, you could use that to kind of evaluate how much, what was the temperature of the material that was ejected from the sun, in this case, because you have the observations. But to take that now and project to something that you cannot validate independently, it's tricky. And so yeah, this is where we need to do better homework. You know, with the solar physicists, we need to figure out what this coronal heating is all about, because we've been promising this since the 70s, that every other mission is going to solve the coronal heating problem, including the probe. But I'm not so sure. But the big picture, we should look at the big picture for the stars. Hopefully, you know, if you average over large areas, that is becoming a little bit easier to handle.
Okay, thank you.
Hi, is it audible now?
Yes, we can hear you.
Yeah, thank you. So I was asking that you have shown in one of your slides about the ejection of flux ropes. I want to ask that what are its consequences in coming years on Earth that we can see it? Is that there will be some other blackout somewhere?
Yeah, I don't have a slide on that, but the consequences, of course, is that these large structures, when they come to Earth, of course, they're much bigger than the Earth, right? Orders of magnitude larger. Now, what they have is that this magnetic field inside and trained into the flux rope could interact with the magnetic field of the magnetosphere. And if they're of the right relative orientation, basically they can reconnect, and the magnetosphere opens and allows solar plasma and particles to enter into our system. And then they themselves, as the system responds to all of that disturbance, then we get all the secondary effects that Yanis knows very well about, that create the impact. So those are, of course, high level. You need very detailed modeling to understand the precise response of the system to the CME. So from our perspective, we take a much simpler approach. They usually consider that if it's a big event, it has a well-defined structure, and is coming, when it comes to Earth, it's at high speed, which means it can compress severely the magnetosphere, exposing a lot of satellites, for example, into the solar wind. We consider this to be a big impact. But of course, when it comes to prediction, of that response, we're not doing extremely well. I mean, we can say, okay, something big is happening, be prepared, but we cannot say to an operator that the next 2 hours, please shut off your satellite, because that would be, we're not there yet. This is a different work that we've been doing.
Yeah, thank you.
Okay. Any other question from the audience? I don't see any hand. So thank you very much, Angelos, again. It was a very enlightening talk, as always. And we do hope to see you again, well, I guess at the latest next summer at Costa.
Oh, yes, absolutely.
At the very latest.
At the very latest. Yes, it was my pleasure. And like I said before, if any of the younger folks have any questions on studies and stuff on the States, they can contact me. You have my email. Yanis has my email. Maria has it. So
Sure.
Yes.
Thank you.
Thanks a lot. Thanks a lot for coming. Yes. And
great to see and hear a lot of you. Thank you. Bye-bye.
Thank you. Bye.
Thank you. Bye, Angela.
Yeah.
And we are going to resume. Yeah, we're going to resume the colloquia on May 19th, because we are breaking for holidays now. So happy holidays and happy Easter.
Happy Easter. Καλό Πάσχα.
Καλό Πάσχα.
Καλό Πάσχα, να είστε καλά.
Γεια σας.
Γεια σας.